Okay, hello everyone. Good afternoon, ladies and gentlemen. Welcome to our presentation. We are going to present our final demo presentation, which is about posture evaluation for weightlifting exercises for human pose estimation models. It's supervised by Dr. Ahmed Rafea. The presenters are Ahmed Ali, Salma Ahmed, Tasneem, Hatem, Zaki Elsayed, and Ziad Elsaid. Our table of contents, first we will discuss the problem statement as well as the hypothesis, and then moving on to the data set. Next, we will discuss the architecture and proposed update, and then the experiments and results with more detail looking into the model accuracy as well as the evaluating exercises. And finally, we will show our conclusion and future work. So the main problem we are addressing here is that since COVID-19 started, many people have stopped exercising in the professional gym setting or doing physical exercises at home instead of in professional setting in the environment of the gym. Thus, they were not getting proper guidance from trainers, professional trainers. Thus, this was causing them a risk of serious injuries from performing exercises in an incorrect manner. So weightlifting exercises can be dangerous. As I mentioned, played incorrectly, so it needs more guidance. Thus, it can be acquired via applications using inaccurate human pose estimation models. So our hypothesis, we have two hypotheses. The first one is creating a new specific data set for weightlifting exercises footages, which will improve the performance of human pose estimation models on this type of specific exercise of footages. And the next one is using multi-scale representation of convolutional layers. Output will enhance the accuracy of prediction of body joints in human pose estimation models. Next, Tasneem will discuss the ZAT dataset.
So we started by collecting videos, YouTube videos. We converted them into frames using an online tool. Those videos are of different variations: video length, quality, work type, angles of view, gym tools, and environment. We ended up with having 2,500 images, 2,100 of which are the trained dataset, and the rest 400 in the dataset, in the test dataset. We used the COCO annotating tool, which has 17 key body joints: the two eyes, the ears, the shoulders, the knee, the hip, the ankle, the elbow, and the wrist. By annotating, we mean that we determine the XY coordinates of each joint and the visibility parameter of it. COCO annotator tool allow us to determine the visibility by three choices. The first is not labeled, and this is in case we have a joint not present in the frame. The non-visible, if it is hidden, the joint is hidden by a wall or a gym tool, and then visible if we can see it. And then Ahmed will continue with the architecture of the human basement.
Okay, so we are talking about why we were interested in collecting the data set in the first place. Actually, we were collecting the data set in order to be able to train different machine learning models in our data set and compare the results and see which model will yield the best results regarding predicting the correct location for each body joint. So after we do that, if we choose as a best model, we could be able to detect the correct angles, since we do that by geometric calculations dependent on the correct location of the points, and that will help us in the evaluation, since we evaluate each exercise based on sum of angles between certain joints. Okay, so now I want to move to talk about some of the machine learning models we have encountered during the year. First, I would like to talk about Alpha Pose framework. Alpha Pose framework actually follows what is known as top-down approach. In the top-down approach, if we have an image with different persons, what happens first, each person is extracted from the image, then separately, each person will have a layer called SPPE, which it shows the position of the key points on the body. So in Alpha Pose, we have an example here. We have an image with different persons. The first one represents different bounding boxes for each person of them. These bounding boxes are an input to a pipeline architecture. This architecture consisted of what's called a spatial transformer network. The spatial transformer network is responsible for enhancing the quality of the image in the first place. Then after the quality is enhanced, we have the SPPE. The SPPE predicts the joints on the body. Then we have the SDTN also for enhancing the output from the SPPE. Finally, after we finish this pipeline, we have what's called pose NMS. The NMS is responsible for remove the redundant key point predictions from the latest pipeline. And finally, as we can see, we have the final image with all the persons. Each one of them is having some lines. This represents the positions of the joints, the points of position of the joints, and also the connection between these points. Okay, so from these graphs, this is the architecture for alpha pose. We were more interested in the SPPE. This PPE, which is a single person pose estimator unit. For alpha pose, they are using something called simple pose. This is the default one as a default layer for the alpha pose architecture. The simple architecture is the one at the right. We can see that it consists of convolution layers followed by the convolution layers at the end for the purpose of the upsampling process. And at the other side, we can see other architecture, one called the hourglass and CPN. Simple baseline says that their architecture is very simple other than the other two architecture, and they at the end perform the same operation as hourglass and CPN. So the two architecture on the left also do the upsampling process, but in more complex calculations. As we can see, we have many different blocks on the right and the left sides, and also we have escape connection layers concatenating with each other, so that will lead to a high complexity. So the simple is a good alternative for these two architecture. But actually, we were not interested in the complexity at our, this wasn't one of our objectives. Our main objective was to enhance the accuracy of the detection of the points. So we thought about replacing simple baseline with other architectures. One of those we encountered was the WASP model. WASP model mainly is a ResNet 101 architecture, but the final convolution layer in the ResNet 101 architecture is replaced by what they call a WASP module. In the WASP module, we see it consists of 4 blocks. Each block have different dilation rate. We have here 6, 12, 18, 24. The dilation rate here represents the upsampling rate. They use dilation other than what we mentioned in the previous slide, which was the deconvolution, which was a simple operation of transposing all these convolution layers. But here they are using another method, which is the dilation. Okay, so why we are using these parallel blocks and why they're taking inputs from each other? They say that this formula would enhance the ability to have a better, a different field of view for the features, and also for increasing the receptive fields. So they take the low features from the ResNet and concatenate it with the output of 4 different blocks, and then this output is passed through what they call a decoder. This decoder consists of the convolution layers and dropout layers. The dropout layers are mainly used for avoiding overfitting and for generalization. And finally, we have at the end a 1-by-1 convolution layer. This 1-by-1 convolution layer is responsible for decreasing the number of channels to the number of classes we have. In our case, since we are detecting 17 key points, so the final output or heat map will have 17 channels, and we can resize the image at the end to revert it to the original size, to be able to have a better results at the end by using something called bilinear interpolation, which revert again the pixels of the image to the original size, which was bought inside the ResNet feature from the beginning. And now Ziad will talk about the results.
So let me take you to the results part. We successfully achieved 90.8% of mean average precision by using alpha pose model and merging it with WASP module, which was described by Ahmed. And we achieved an increase in mean average precision of 8.52 by training this model on our training dataset. So let me clarify these numbers to you through this table. We firstly, I want to explain what is fast pose. It's an alternative for simple pose. It's an SPPE, so it's also part of alpha pose. So we are using the same framework in all experiments. The different thing is the SPPE. So we have simple pose and fast pose and the new proposed alpha pose, which is the WASP module. The first experiment, we used COCO training dataset as our training dataset and the COCO test dataset as the test dataset. We achieved 70.6 MAP on simple pose and 71.7 on fast pose and 73.4 on WASP. The second experiment, we used also COCO training dataset as the training dataset, but now we changed the test dataset to be our new test dataset, which is called the ZATS. As you can see, there are better results because our test dataset is much smaller than the COCO test dataset. However, this is not the best results because, as you can see in the third experiment, we are using the training dataset, which is our new training dataset, and we have the weights of all of these model pre-trained on COCO training dataset also. And we are using our test dataset as the test dataset of the training. So we achieved 90.2 on simple pose and 89.7 on fast pose, and we achieved the highest accuracy using our new proposed architecture, which is WASP. We got 90.8 MAP. So we achieved what we were aiming to get in our hypothesis, and this will help us in the second part of our research, which is evaluation of the exercise using calculation of angles, as Ahmed said. And now I will explain how this will help us. Okay, so as you can see, we are calculating the angles by taking the XY coordinates of 3 joints, and we got the angle between them. So if a joint is wrongly positioned, so the angle will be wrong, then the evaluation will not be accurate. This photo is taken, it's a frame taken from a video of me doing squat workout. I am intentionally doing it in a wrong way. I'm bending my back. So we can observe if the model can give a feedback that there is an error and how to correct it. So this photo is generated, the pose estimation here is generated by a model trained on ZATS, which is our new dataset, and COCO training dataset. And this the pose estimation is generated by a model trained by only COCO training dataset. So as you can see, there are some joints which are incorrectly positioned, such as the hips, shoulders, and the elbows also. But here they are almost correct. And here the feedback is saying to go on. So this is because the wrong position of shoulder and hip, which makes the angle more than the right one. So the model can't detect that the angle is smaller than the normal range. So the model doesn't know that I'm bending my back. So the prediction here is false positive because here the right feedback is I should straighten my back. This is another example of me doing biceps curl correctly now. So also we have two frames. One of them, the pose estimation generated by ZATS and COCO. The second one, COCO only. We can see in this one, which is generated by COCO only, the left elbow is positioned incorrectly. It's above its original the right value. So the angle between the elbow and shoulder and hip is larger than the right one. It should be less than that. So it's giving a feedback to move my left elbow closer to my body. However, it's already close to my body and I'm doing the exercise correctly. So this is a false negative prediction, and so this is the right feedback to go on. So now Zaki is going to talk about the common errors and how we will calculate the accuracy of our evaluation.
In this table, we have listed the errors which is observed from each exercise, and moreover, we are going to seek an expert trainers in order to evaluate our videos and give us feedback. And also, we contact another expert trainer which will help us in supervise the accuracy calculation of feedback given from the model and the trainer, and choose which one is the right. This will be done to fill the confusion matrix of the model evaluation, so we can calculate the recall and precision and the total accuracy of the evaluation. Coming to the demo part, we have created a simple interface to test our model. And as we could see, we have here 5 different workouts: shoulder press, squats, deadlift, and biceps curl, and lateral raise. Each workout is target different muscle. And now in this demo, we will go more with the biceps curl to explain it, the model. As you could see here on the screen, the left progress bar is an indicator for the right arm, and the right progress bar is an indicator for the left arm. When it reaches 100%, it means that the user has reached its maximum point, so he has to return back to its starting point by reaching it to 0%. And as we could see on the top of the screen, there is a message which is displayed in the blue color, which tells the user go on. It means that there is no any incorrect movement, and he can continue his workout normally. And also, we could see here 4 sentences in red color, and it starts with the letter R, which means the right part of the body. And we could see here the first letter in each word is an indicator for the muscle. For example, WES for the wrist, elbow, and shoulder angle. And also, it displays the angle measurement on the screen to help us know whether the trainee is performing the exercise well or not. And the below is for the left part of the body, and here we could see the knee tensor X coordinate and the shoulder also. And now Ziad will start to perform the workout. It displays go on, so there isn't any mistake. And now it tells raise your right hand up, as his right hand up is out of the range of motion, so he has to correct it in order to be able to perform it correctly. And also, he will try to do more than one mistake to evaluate our model. And it will be displayed for while it displays red, it means that he has to stop and modify his posture. Tasneem will continue.
We came up with 3 conclusions. The first one is that the data set improved the precision of the pose estimation model. Therefore, we have improved the accuracy of the pose estimation model. Our human pose estimation model. Using WASP instead of deconvolutional layer improves the accuracy of human pose estimation model. And the third one is evaluating the accuracy of exercises by calculating angles can be done. However, there will be presence of many limitations. And from here, we'll go to the future work. Improve the evaluation method to overcome the existing of limitations. Second, try to implement pose estimation models with lower complexity. This will allow us to create mobile applications and make the user interface more friendly. And then we will expand our data set. Here are our references, and thank you.